Next, we want to look at contours on this plane to better understand the velocity profile. We can create a new contour plot as before by selecting Contours under the Results tab and clicking New. Name this Velocity ZX. As before, change Contours of to Velocity, and ensure Velocity Magnitude is selected. In the Surfaces list, select only ZX Offset. And click Save/Display, and we can close this window. In the view, we can see contours on this plane. Ensure you are facing the XZ plane by clicking the Y-axis in the bottom right, and click the Fit to View button on the left to adjust the scale. Here, we can see the flow as it moves around the obstruction. We can see the flow is slowed as it approaches the cylinder and reaches a stagnation at the frontmost point, as seen in the velocity vectors. Away from the cylinder, we can see that the velocity increases slightly as the flow moves around it. The cylinder effectively reduces the flow area and therefore increases the speed. This occurs symmetrically from top to bottom as expected. Downstream, the contours return to a more normal profile. Interestingly, if we zoom in, the profile looks nearly symmetric from front to back as well, with the low velocity stagnation region in front of the cylinder being matched with a very similar region behind it. This is characteristic of low Reynolds number flow, in which viscous forces dominate and the boundary layers stay attached. This means that the flow does not separate and recirculate behind the cylinder. As the velocity increases, we would expect this rear low velocity region to grow as the flow separates. Near the walls, we can again see the boundary layer development, which works to shrink the flow area and increase the velocity. We can similarly investigate the pressure by creating a new contour plot as before. Name this Pressure ZX. Change Contours of to Pressure, and ensure static pressure is selected. Ensure only ZX Offset is selected in the Surfaces list. And click Save/Display. We can then close the window. In the view, we can then see contours of pressure. Near the inlet, we can see the high pressure regions seen on the inlet contours at the top and bottom corners. These are local artifacts of the boundary conditions and can therefore be ignored. To remove them from the contours, as well as better highlight the high pressure regions of the flow, under Contours in the tree, right-click on Pressure ZX and click Edit. Back in the pop-up window, uncheck Global Range and Auto Range. Then, we can change max to 5 pascals. This adjusts the range of pressures plotted in our contour plot and helps to remove unintended outliers as well as better highlight the true contours of the flow domain. Click Save/Display to view the changes, and we can then close this window. In front of the cylinder, we can now more clearly see that the pressure increases slightly as the flow is slowed, as predicted by the Bernoulli equation. Unlike the velocity contours, however, there's no symmetry between the front and rear of the cylinder. As the fluid moves around the obstruction, it experiences viscous losses that decrease the pressure. This is not accounted for in Bernoulli's equation, leading to the discrepancy. This creates a low pressure region behind the cylinder that produces a net drag force on the obstruction. We can also see that, away from the cylinder, the pressure looks largely unaffected. We can see the apparent symmetry about the axial z-axis seen in the previous pressure contours, in which the pressure decreases over time but remains constant along a cross-section. Another useful visualization is the wall shear on the boundaries of the model. This is important in understanding the effect of the flow on the bone structure and the forces caused by the velocity gradients in the flow. To investigate this, create a new contour plot as before. Name this Wall Shear. Under Contours of, select Wall Fluxes, and ensure Wall Shear Stress is selected. In the Surfaces list, ensure only Wall Inner is selected. And click Save/Display. We can then close this window. In this view, we can see the wall shear on the inner surface. The largest band of high wall shear occurs near the inlet. This is an artifact of the high velocity gradients near the wall caused by the boundary conditions and is just a local problem, as seen in the velocity and pressure contours. To better see regions of high wall shear stress, we can adjust the range of plotted values as before. In the tree, right-click on Wall Shear and select Edit. In the pop-up, uncheck Global Range and Auto Range, and enter 0.5 pascals for max. Click Save/Display to apply the changes, and we can then close the window. We can now more clearly see the wall shear trends near the obstruction. Click on the y-axis in the bottom right to face the plane if necessary, and click the arrows to adjust the orientation. Adjusting the view can sometimes cause the visualization to have rendering issues. This can be fixed by clicking the Fit to Window button on the left side of the view pane and clicking the Zoom to Area tool to zoom when necessary. We can then left-click and drag to select the area we want to zoom in on. Near the obstruction, we can see that the wall shear is low in front of and behind the cylinder. This makes sense given the low velocity gradients seen in the previous contours. Above and below the obstruction, however, the wall shear is amplified to values beyond the fully developed regions downstream. This shows the effect of the obstruction in the domain. With more pillars, we can expect this amplification to increase further. Beyond the obstruction, however, we can see that the wall shear is effectively constant on the inner surface. Right-clicking to inspect the values, we can see that the wall shear is elevated to around 0.42 above and below the cylinder, before returning to a more standard value of 0.36 to 0.365. Finally, we can investigate the mass flux at our inlet and outlet boundary conditions. In the Results tab, under Reports, select Fluxes. In the new window, ensure that Mass Flow Rate is selected under Options, and select Inlet and Outlet under the Boundaries list. We can then click Compute at the bottom. The results are visible in the list on the right. A positive value indicates flow entering the surface, while a negative value indicates that it's leaving the surface. We expect no mass accumulation within the structure, so these values should be very close. We can see the difference between these values under Net Results. This value is extremely small, indicating good convergence. We will look at this result more closely when verifying our solution. So we can close this window. With this completed, make sure to save your project. If prompted, select Save Changes for current and future calculations to preserve your work, and click OK.